Hi everyone and welcome back to PrepFusion. I'm Anish and today we will start with the assignment questions that we discussed, like that I gave you as homework in the previous lecture. So this was the first question, and if you were trying to solve this first question, I think you would have found out that you will not be able to find out the z parameters. Why? I will explain. So here this is a transformer, and what is the relationship of a transformer? We know a very basic relationship of a transformer, that your V1 or V2 by V1 will be the turns ratio, right, across that particular winding. So what are the number of turns here? N. Number of turns here is 1, so it is n is to 1, so this will be n by 1. N by 1. Okay. What about the current? So current turn ratio is the opposite, right? So it is I1 by I2 equals to n by 1. Okay. So these are the turns ratio basically. So, but remember, this is not exactly correct, right? This is not exactly correct, because in a transformer, the currents are shown like this. The currents are like this. If this is the voltage, this is the current I1. Current of the transformer, right, is I2 dash here. Current of the transformer is I2 dash on the right hand side. It is not like it is incoming. Okay, it is outgoing. If you have seen the currents of a transformer, it is outgoing. So this relationship is not exactly correct for the current. Voltage, it is correct. Voltage, it is correct. For current, right, what we write is I1 by I2 dash equals to n. And what I know about the current I2, so I2 is equals to minus of I2 dash, because both I2 and I2 dash are in opposite direction. So I2 will be equals to minus of I2 dash. Got it? So actual relationship between the I1 and I2 will be like this. So I1 by minus of I2 will be equals to n, or I can write that I1 by I2 equals to minus of n. Okay. So now let's find out the z parameters. So what is z11? Z11 is V1 by I1 when I2 equals to 0. So V1 is V1 is V1 only. Okay, V1 is V1 only. And what is I1? I1 is actually minus n of I2. Correct. So this I can replace with minus n of I2, and in the equation I have to put I2 equal to 0. So V1 will be some finite value. Finite upon 0 will yield my Z11 to be infinity. Okay. So something is fishy here, right? Something is wrong. So same thing you try for Z21. Okay. What is Z21? Z21 is V2 by I1 1 by I2 is 0. Same thing again. It will be V2 divided by minus of n I2. Again, of course, you make I2 0. So again your Z21 is also tending to infinity. Okay. Then I have Z12. Z12 equals to V2 by V2 by I2. Again the same thing will happen. Sorry, V1 by I2. Same thing will happen, that you will make I1 0. So basically your it is V1 divided by minus of, this is I1 by n. So I2 will be minus of I1 divided by n. So your I1 is equals to 0. So again it is tending to infinity only. So everything, right, your similarly your Z22 will also tend to infinity. So of course what is happening in this case, the Z parameters does not exist for a simple transformer. Z parameter does not exist for a simple transformer. What went wrong? The thing that I told you, right? Z parameters in the previous lecture, I told you, if the two independent variables, that is I1 and I2, are dependent on each other, then Z parameter will not exist. Okay, because here my I2 is a function of only I1 and my I1 was a function either or, like both are saying the same thing only. I1 is a function of only I2, then basically your Z parameters will not exist. Not exist. Okay, so in these kind of cases, Z parameter will not exist, right? This I have already written in the key points in the previous lecture. So now try this question. So just pause the video and tell me, will the Z parameters exist here or will the Z parameters not exist? So that is for you. So like one modification I want to make, this I2 current, right? This I2 current is not exactly here. This I2 current is actually here. That was my bad. I forgot to change it over that in the lecture. This will be the arrow. I2 current will be here. Okay, that was my mistake. It will be on the outside. Okay, so now if you find out the parameters, so for this, right, I will just tell you at the starting itself that the Z parameters will exist. Okay, because here, right, my I1 is not directly a function of I2. Yes, the transformer internal currents are function of each other, that is correct, but we are not discussing about the transformer internal currents, right? We are discussing about the I1 I2, the port currents. So these two things are important, are different. So I will copy this circuit here. Okay, and then, right, I will change the names because you might have a bit of doubt. So basically, what are my port currents? So I will first of all delete this thing. Okay, so I have two types of current here. I have two types of current here. Okay, so two types of current are there. So one is this current, that is the port current I1. Okay, another one is the other current, that is I primary current of the transformer. Here also I have another current named as I secondary, the secondary current of the transformer. Okay, these things are different. I secondary and I2 are two different separate currents. Okay, now you can write the relationship for the transformer current. So I know the relationship for the transformer current is I secondary upon the I primary, that is equals to the opposite turns ratio. It will be 1 by n. Okay, this I know, and the voltage relationship is still there, but uh, I have not told you that impedance parameters will not exist if voltage are directly related. If voltages are directly related, I have not told you that you will not be able to find out the impedance parameter. That I have not described, right? So no, that does not matter. So here V1 by V2, which is correct, are my port voltages as well. The transformer primary voltage V primary and the transformer secondary voltage V secondary are the port voltages as well. So V primary divided by V secondary will be equals to 1 by n. Okay, but which is equals to V primary is equals to V1 only and V secondary is equals to V2 only. Okay, so now we can solve, right? So we have to find out the Z parameters. So as I have to find out the whole Z parameters, so I will use the I will take the help of KCL and KVL. Okay, so if I observe that I primary is same as I1. Okay, that I know. And if I apply a KCL in this node, if I apply, so what I will be able to find out is that this current, right, this current is equals to what? This current is equals to, this color is not great, this current is equals to I2 plus I secondary. So if I primary is equals to I1, so this equation will be I secondary will be equals to I1 by N. So I can replace, because I primary is I1, I can replace here I secondary as I1 plus N. So this current, right, this current will be I2 plus I secondary, or I2 plus I1 plus I1 divided by N. Now what is the voltage drop V2? Voltage drop V2 is the voltage drop across this resistor. So V2 equals to I2 plus I1 by N, the current, into the resistor R. So V2 equals to I2 into R plus I1 by N into R. So from here you can directly say what are my Z21 and Z22. So Z21 and 222 we have found out. What about Z11 and 12? So very simple, right? Because I know V2 equals to V1 into N. V2 is equals to NV1. So if I just replace V2 here, NV1, I will be able to find out the Z11 and Z22 as well. So my V2 will be NV1 is equals to I2 into R plus I1 divided by N into R. So V1 will be equals to R by N square into I1 plus R divided by N into I2. Okay, and like from here you can directly say what is my Z11, this is my Z11, this is my Z12. So here, right, they will exist because my I1 is not directly some function of I2, right, because there is some secondary current, all those things are there. So that's why Z parameters will exist. So my Z matrix I can write as Z11 will be R by N square, R by N. Okay, and Z21 will be R by N again. Again it seems like it is a reciprocal network because Z12 and Z22 are same, and Z22 will be R. Okay, and you might feel like the unit of Z parameter is ohms. So is it different here? It is same, right? N is just a quantity that is unitless. So if I divide and multiply by N, it does not change the unit. So unit here is always R. So like this also you can cross verify whether you are correct or not. So I see all the units are in ohms. So you can cross verify whatever you have solved is correct or not just by seeing the units. So everything is in proportional to resistor. So whatever you have solved is totally correct. Okay, so yeah, that was about this question basically. So let's move on to the next question. So we will solve few questions. So this is the next question. So here we have to find out the Z parameter. So I am using directly method 2, I am not using method 1 because I have to find out the Z parameters, overall Z parameters. So individually I am not finding it out. Okay, so again in this, right, simply I can again copy this network and write to KVLs. So seems like a complex network but is really a simple network. So this is the first KVL I1 and this is the second KVL I2. So my minus of V2 plus I2 into okay, I'm using the second KVL, so any KVL you can start. And what is this current? This current is what? This current, right, will be I1 plus I2, because I1 is incoming here, I2 is incoming here. This current will be I1 plus I2. I2 into 1 plus I1 plus I2 into 2, and don't forget this 10-volt source as well, right? So I hope whatever reference you follow KVL, you can follow that reference. I follow this reference, that I always write the first sign. I always write the first sign. Drop is like this, so I will always write the first sign in my KVL. Okay, so this will be 10 and then equal to 0. So from here your V2 will be equals to V2 will be equals to uh, V2 will be equals to I1 2I1 plus 3I2 plus 10 is also there. Now, right, in these kind of cases you will not be able to find out the Z parameter. Why? Because my Z parameter did not have any constant term, right? It had only coefficients of I1 and I2. So this is a constant term. Okay, and I will say you, for these kind of networks, right, Z parameter cannot be defined. So if I have an active source inside the network, I will not be able to model that. So make sure to deactivate the sources. So same KVL if I write, this is the KVL 2 and the same KVL 1 if I write, okay, this will be minus V1 plus I1 plus I1 I2 into 2 plus 10 equal to 0. Again the same thing will happen, that my V1 equals to 3I1 plus 2I2 plus 10. Okay, so ultimately what I can comment is that again it is a constant term present. So for these kind of networks, right, Z parameter cannot be determined. So Z parameter cannot be determined for non-linear networks. So this is a non-linear network because I have a source inside the network. This is my network, right, and inside the network I have a source, so it becomes non-linear. So I will write here, very important point, Z parameters or any parameter for the fact of the matter, or any other parameter, whatever we will learn, meters cannot be determined for non-linear networks. Okay, so yeah, just be careful about this. So now we have this pi network. So for this pi network, again you can derive a formula. You can solve, like, method 1 is basically you can convert this thing, right, into star network, because it is very easier to find out the Z parameters for a star network. So convert into star network, that is the method 1. So basically, right, this circuit can be converted this circuit can basically be converted into star network. So I will have impedance here, and like this is a common point, right? So after solving for the star network, you will simply be able to find out. So this network will be converted into a star one, so it will be a T network, right? So it will be more like a T network. So my impedance will be here, this will be my z3 dash. Okay, this will be z3 dash, z3 dash, and this will be my z1 dash, z2 dash. So like I hope you remember the star to delta formula. How I used to remember is I have to convert from delta to star. So star, right? Star has the first term as sorry, delta to star. So delta, the first term has the first letter as D. D means division. So that is how I used to remember. D for division. So of course I have to divide. What is the division? Division, if you remember, I remember in the division formula all the sum used to come, right? This z1 plus z2 plus z3. So it will be z1 plus z2 plus z3, and at the top the opposite impedances. So for this one, right, z1 z1. So for this one, these two are the opposite ones. So it is z1 into z2. So it will be not the opposite ones, sorry, the adjacent ones, and this will be z2 dash. So z2 dash, z2 dash will be uh, this one, right? So this one has the adjacent impedance as z1 into z3, z1 plus z2 plus z3, and same for z3 dash. Z3 dash has the adjacent impedance as z2 and z3. Okay, so it will be z1 plus z2 plus z3. Okay, so yeah, these are the like impedances basically. I hope you have understood these things. So this is one of the way which you can solve. Or method 2 is simple KCL you can apply, right? Method 2 is simple KCL and KVLs you can apply. So method 2 is KCL. Okay, so I'll copy the circuit, copy this circuit, paste it over here. So here what we can say is that uh, I can apply a KCL here, I can apply a KCL here. So this voltage is V1, correct? This voltage is V2. So this is the node 1, this is the node 2. So let's do the KCLs at node 1 and node 2. So node 1 KCL I'm finding out. So it is V1 divided by Z2, V1 minus 0 divided by Z2. 0 is the reference point, right? This is the ground. Plus V1 minus V2 divided by Z1 plus, sorry, minus I1 equals to 0. Okay, and this will be V1, I can take common, so 1 by Z2 plus, okay, let's not do this, let's keep it as it is. In the node 2, let's do the KCL again. So this KCL will be V2 minus V1 divided by Z2. So what I do is, right, I take the outgoing currents as positive and the incoming currents as negative. That is my convention of KCL. Okay, your convention may be something else, but ultimately you'll reach the same answer. Okay, your convention may be something else, but answer will be same ultimately. So V2 minus V1 divided by Z2, then I have V2 minus 0 divided by Z3 plus V2, sorry, plus sorry, minus I2, because I2 is incoming current. So right, if I add these two equations, what will happen? This and this will get cancelled. Okay, or should I have to write this in terms of V1 and V2. Okay, if I add these two equations, this and this will get cancelled, but V2 will be still here, right? Somehow I have to eliminate V2, that is not of much use. So let's do one thing. Let me eliminate V2 from here, because if I eliminate V2, then that will be the end of everything. So In the second equation, this is the equation 2 and this is the first equation. Okay, equation 2 and first equation. So this will be V2 by V2, if I take common, 1 by Z2 minus V2 plus 1 by Z3, and on the right hand side I have V1 by Z2 plus I2. Okay, V1 by Z2 divided by I2. So this will be V2 equals to V1 divided by Z2 into Z2 Z3 divided by Z1 plus Z2. Same here as well, right? I2 Z2 Z2 will get cancelled. It will be Z2 Z3 divided by Z1 plus Z2. So Z2 Z2 will get cancelled. So only Z3 by Z1 plus Z2 will be there. So this V2, right? This V2 I can replace here. Okay. So first let me write this V1 in terms of V2 and I1. So this was the equation 2. Let me rewrite the equation 1. So equation 1, this will be V1 by Z2. V1 divided by Z2. So V1 by Z2 plus, and okay, this is V1 by Z2 plus V1 by Z1, 1 by Z1. Okay, and this is V2 by Z1, V2 by Z1 plus I1. Okay, so my V1 equals to V2, this Z1 will get cancelled. This will be Z2 divided by Z1 plus Z2 plus I1 into Z1 Z2 divided by Z1 plus Z2. Now I will replace my V2 here, right? So this will be a bit lengthy. Okay, a lot of things will be there. So I will replace my V2 here. So if I replace my V2 here, right? So what is V2 equals to this mess? It is a mess, right? It is a total mess. So okay, this is Z1 plus Z2 is also here. Huh? No, this should not be. Sorry, this is Z1 plus Z3. Sorry. This is Z1 plus Z3. Sorry, this is Z1 in plus Z3, Z2 plus Z3. Okay, so ultimately, right, if you solve the equation, you will get some values. Okay, I don't care. Okay, you will get some values. Through that you can basically find out. So you put this V2 value of V2 here from this, right? You put the value of V2 in this equation and you will get back your VM. But this is lengthy, right? So the approach 3 is better to solve individually. That's why sometimes I told you that this approach is better. Now what we do is, let's first find out Z11. Z11 is V1 by I1. Okay, so that is I2 equal to 0. So this will be open circuited. This is open circuited. So this is open circuited. So basically, right, these two circuits are in parallel with each other because this is some current I1 dash, this is some current I1 double dash. So current division is simply happening here because these two are in series here. Okay, so basically the current I1 dash equals to V1 divided by Z1 plus Z2, and current I2 dash, I1 double dash equals to V1 divided by Z2 only. So this is Z3. Okay, so I hope I have not made any mistake previously as well about Z2 and Z3. So I know that my I1 current is I1 double dash plus I1 dash. So it will be equals to V1 into 1 by Z1 plus Z3 plus 1 by Z2. So from here, right, you will be able to write your uh, parameter basically, or you could have directly seen what is V1 by I1. It is the resistance or impedance seen from these two nodes, right? So it is basically Z2 parallel with Z1 plus Z2. So like that also you could have written that your V1 by I1 is just impedance. Of course, there is a condition attached. After attaching the condition, what is the impedance that I am observing? It is simply this Z2 parallel with the series combination of Z1 plus Z3. So it will be Z2 parallel a series combination of Z1 plus Z3. Okay. Of course, there is a condition where my I2 is 0. So this was the Z11. Okay. What about the Z12? Or let's find out Z121. So Z21, for that you have to write down equations. Okay. So Z21 is basically the voltage across the, like Z21 is V2 upon I1. V2 upon I1, right? So let me apply the current division rule. Okay. So what is this current? I1 dash. If I apply the current division rule, I1 dash in terms of I1, if I want to write, it will be what? The opposite impedance upon the overall impedance. Okay. So opposite impedance is Z2 upon the overall impedance, that is Z2 plus Z1 plus Z3. So this is my I2 dash, and what is my V2? V2 is simply not I2 dash, sorry, I1 dash. V2 is I1 dash into Z3. V2 is I1 dash into Z3. So it is I1 dash into Z3. So I1 dash will be I1 into Z2 divided by all of these things. So it will be I1 into Z2 Z3 divided by Z1 plus Z2 plus Z3. So your V2 by V2 by I1 or Z21 will be this Z2 Z3 divided by Z1 plus Z2 plus Z3, given of course that your I2 current is 0, provided your I2 current is 0. Okay, so like I hope you can understand how simple it is to calculate the quantities individually. So that's why, right, you have a trade-off. If the circuit is simpler, you can use that method, solving everything together. If the circuit is difficult, you have to use this method, solve one by one. Circuit will be simplified, and the simple circuit will be much easier for you to solve. So again, for the other part, that is making the I1 0, if I make the I1 current to be 0, then same thing you can see that your V2 by I2 will be the Z22, correct? Your V2 by I2 will be the Z22. Z22 will be V2 by I2 when I1 is 0. So simply, right, these two will be in series in parallel with Z3. So it will be Z3 in parallel with series combination of Z1 plus Z2. Okay, and what about the Z12? As it is a reciprocal network, it will be same as this one, Z2 Z3 divided by Z1 plus Z2. Of course, you can calculate. You can of course calculate. You will verify that you are getting the same answer. How is it reciprocal? Generally, a resistive circuit or a circuit of a passive circuit is in most cases is reciprocal. Generally, a passive circuit in most cases is reciprocal. Okay, so this will be when my I1 equals to 0. One more thing I forgot to tell, like your Z parameters will not exist here. Z parameters cannot be determined for non-linear networks where basically independent sources are present. If dependent sources are present, then of course you will be able to find out the Z parameters. If independent sources are present inside the circuit, then you will not be able to present. So for dependent source, you will be able to write down the values because your dependent source depends on the value of current or voltage in some branch, right? So it will not be a constant term. Okay, it will be something proportional term. So that's why for dependent sources you will be able to find out the parameters, any parameters, y, z, any parameters. Okay, so this was basically the way to find out, and another way is there, okay, that we will learn, of course, method 4, the last method, that is using y parameters. So this we will learn later on. So basically you finding out the y parameters for a pi network is much easier, just like for a star network or a y network, finding out the z parameter is very easy. Same applies here. So we will learn this, don't worry, later on we will learn this. So after you find out the y parameter, your z parameter is just the inverse of the y parameter. And don't worry if you don't understand this, we will learn about this. Given, of course, this will be always valid, this will be always valid, we will learn about this, don't worry, we will learn about this. This will be always valid unless and until, like, until your determinant of the y parameter matrix is not equal to 0. If it is 0, inverse does not exist, I will not be able to find out the y parameter. This we will learn later on. Okay, so we will learn about y parameters later on. Now let's calculate this values, right? Basically this I1, like this port currents I1 and I2. If the z parameters are given, how do you find out the port current? So this also we will learn basically. So here, right, what you have to do is you are given the z parameters. So first you will write the equations. First you will write down the equations. So let me write down the equations first. So z parameters are given. So v1 and v2 will be here in terms of I1 and I2. So this Z11 will be with the I11. So this will be 6 into I1 plus this Z12 will be with respect to I2. So this will be minus of J4 I2. This Z21 with respect to will be with respect to I1 only for V2 plus 8 of I2. So these are my equations. Okay, so what are they asking? They're asking me to find the port currents I1 and I2. Okay, because there is some voltage given, right? So I will be able to find out the port currents. So can I apply a KVL here? Yes, I can, right? So this KVL will be minus, like I always in my KVL, I always write the first polarity. Okay, so minus 2 first polarity that I encounter, minus 2 angle 30 plus I1 into 2 plus V1 equals to 0. So from here I get another equation for V1. V1 is equals to 2 angle 30 minus 2 I1. Okay, so V1 equals to 2 angle 30 minus 2 I1. So now what I can say is I can replace this value here. What is V2? V2 is just short circuit. So if V2 is just short circuit, that means my V2 is simply 0. V2 is simply 0, correct? V2 is just short circuit, right? It is shorted, so it will be 0. So I can replace this value. So 2 angle, first let me replace it here, this is easier. So 0 is equals to minus J4I1 plus 8 I2. So your like I can directly write my I2 will be equals to J divided by 2 I1. Okay, what about this V1? So V1 I can replace with 2 angle 30 degrees minus 2 I1 equals to 6 I1 minus J4 I2. Okay, so from here I know what is my J4 I2. So J4 I2, right? So if I multiply this with J and then multiply with 4 I2 on both sides. So this will be j square 2j square. So this will be minus 2 I1. So this can be replaced with minus 2 I1. Already here a negative sign is there. So this overall thing will be here 2 angle 30 equal minus 2 I1 equals to 6 I1. So this will be plus 2 I1. Okay. So overall this will be 10 I1 equals to 2 angle 30, or I1 equals to 1 by 5 angle 30. So I got my I1 current. So you can simply find out your I2 current as well, right? You can simply find out your I2 current as well. So yeah. So let's basically solve this question. So this is 2 angle 30. So I2 current will be what? I2 current will be just j by 2 of this I1. So it will be j is what? J is 1 angle 90 divided by 2 into I1. I1 is 1 by 5 angle 30. So I2 will be equals to 1 by 10 angle 120 degrees. So this is my I2 and that was my I1. So that's what like these are the type of questions that generally comes. Okay, so now let's find out the Z parameters for a single element. So this is a single series element, series component, and this is a shunt element. So will the Z parameters exist? We'll see. Okay, so in this case, right, my I1 is directly equals to minus I2. I like here I1 is coming, here I2 is coming. So in the first case, in the case one, my I1 is directly equals to minus I2. So from this you can directly say your Z parameters in the case one, Z parameters does not exist. Okay, Z parameter does not exist if I1 is function of I2 or something like that. Of course you can verify this, right? So what is your V1? V1 minus V2 equals to V1 minus V2 divided by Z equals to I. Z2 divided by Z equals to I1. So V1 minus V2 equals to I1Z. And on from this equation, what you can write? From the other one, V2 minus V1, V2 minus V1. Like basically you will not be able to do this. Why? Because like let's find out Z11. What is Z11? Z11 is V1 divided by I1 when I2 is 0. So if you make I2 0, right? If you make I2 0, that means this terminal is open circuited. If I2 is 0, I1 is also 0 because they are in series. So if I1 is 0, this will be some finite voltage upon 0. So that will yield infinity, right? Same you can derive for the other Z parameters as well. Ultimately, you will get infinity. Okay. So let's move on to the next part, that is the shunt element. So shunt element, will the Z parameters exist? Yes, Z parameters will exist actually, because here my I2 and I1 are not totally dependent on each other. Okay, so so uh, so basically here, right, I can use again 2 KVLs. It is just like a modified star network where these impedances are 0. So it even simplifies. Circuit is even simplified. So here it will be V1 will be equals to I1 plus I2 into Z. So V1 is equals to I1Z, because this whole voltage is across V1, correct? I1Z plus I2Z, and same for V2 as well. V2 is equals to I1 plus I2Z, and it is fine. Z parameters the individual elements can be same, there is no harm in that. Okay, they can be same. So this will be I1z plus I2z. If here, right, basically my z parameter is z z z z, these are my z parameter basically. Like this is a very very bad name because z is here, z is here as well. Okay, so this is the z parameter for a shunt element. Okay, so like one important fact, of course, if z12 is equals to z21, it is reciprocal. Another important fact that obviously we will discuss later as well, that if z11 and z22 are same, basically it is a symmetrical network. This is the condition for reciprocal network. And this is the condition for symmetrical network. Okay, what do we mean by symmetrical network? Basically, if I apply some voltage here, whatever current I will see, same if I apply the same voltage on this port 2, I will see the same current. Basically, it is symmetrical about the middle. So if I from the middle, if I cut this in half, if I see on the left and if I see on the right, the network will be identical. So how can I cut it in half? Because this z, right, how can I cut it in half? So this z can be replaced with a parallel combination. So you can replace this z with a parallel combination. So the z can be replaced like this. Okay, so this will be what, z 2z into 2z. Okay, so now if I cut this in half, correct, about the middle, about the center. So if I cut this in half, if I see on the left hand side, whatever I will see on the left hand side, same elements I will see on the right hand side. So if it is totally symmetrical about the middle of the network, then this condition will be satisfied. Your z11 will be equals to z22. Okay, so let's we are just getting used to solving the z parameters for very predefined networks, so that in the examination, if you are getting asked to find out the z parameters, it should be cakewalk for you. It should not be very difficult for you. Okay, so like again, you can solve this using many methods. Either you can divide this network, right, you can convert this network into bridge circuit. You can convert this network into bridge circuit, or you can directly solve using KCL and KVLs. Okay, so let's convert this network. If I want to convert, okay, let's not convert anything, right? Like there is a equivalent circuit of this, so I will explain what is the equivalent circuit, and we will solve without the equivalent circuit. So this network, right, can be converted like this. So okay, so and here I will have okay, so I will just make the network, then I will explain. This is fine, these will be here. Okay, so basically, right, all of the points can be converted into bridge network. So if this point is, let's name the points A, B, C, D. So the outer points, right? These are my port points basically. This is the point of A and B. So V1 is getting applied here. Okay. So this is the place where V1 is getting applied. V1, and these will be the other points. This will be the point of okay, no, sorry. AB is between this, right? So I should rename the points. Let me name this as AB and CD. Okay, so AB is here and CD is here, and this is the output voltage V2. And now we will write down the impedances. So this, right, between A and C there is impedance called Z1. So between A and C there is impedance called Z1. So this will be Z1. Okay. Between A and D, there is impedance called Z2. Between A and D there is impedance called Z2. Okay. Now between between A and B there is nothing. Between B and C there is impedance called Z2. So between B and C, so this is the impedance Z2 here, and between B and D there is impedance called Z1. So between B and D there is impedance called Z1. Okay. So now you can solve. Okay, you can solve using this method. What is I2? I2 will be the current from the positive terminal of V2, and what will be I1? I1 will be the current going out from the positive terminal of V1. Okay, you can convert, but without converting, I will directly calculate. Without converting, right? This is the conversion. Then you can follow along my method, but without converting, right? Few students will not be comfortable with conversion. So without converting, I will solve. Without converting. Okay. So of course you can follow along with the conversion as well. You try. Okay, that is for your assignment. You try with the conversion. Okay, both of the circuits are totally identical. So we will calculate separately here because the circuit is very complex. So I will use that method separately. So here my what I can say is, first I will calculate for Z11 and Z21. So for Z11 and Z21, basically we have to make the I2 0. So if I make I2 0, basically these two elements are in series, and here I2 is 0, right? So these two elements are also in series. So both of them are in series. So I have to find out the V1 by I1. So V1 by I1 will be the input impedance seen from this two nodes A and B. So these two are in series and these two are in series. Okay, and ultimately these 2 points are in parallel. So basically this circuit, right, can be converted like this. So here I will have this A and B point where this will be the equivalent impedance, that is Z1 plus Z2. Again the other impedance can be converted here as Z1 plus Z2. Okay, so now if I write the equivalent impedance, basically your Z11 will be the parallel combination of Z1 plus Z2, that is Z1 plus Z2 divided by 2. So this is the ratio of V1 by I1 input impedance when I2 is 0. When I2 is 0. Okay, so yeah, now we have calculated. Now what about the other impedances, right? So what about Z21? So Z21 is what? Z21 will be a bit difficult to calculate. V2 by I1 when I2 is 0. Okay, so I have to calculate V2 by I1. So basically this is my V1, right? So this voltage is across this Z1 plus Z2 combination and across this Z2 plus Z1 combination. So if I break down this voltage, because these two are in series, so let me mark the voltages here. So let me say this is the voltage, what? This is the voltage VCB, and this one is the voltage as VAD. Okay, and this one is the voltage as VBD, and this one is the voltage as VAD. Okay, and let me mark this separately because current is flowing like this, right? Because V1 is activated, so current will flow like this. So let me mark the positive terminal on the right hand side, plus minus V dB, and current will flow like this. Okay, fine, like this. Current will flow like this. Okay, okay, for this case it will flow like this. Okay, 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 anyway works, that's fine, anyway works. So basically, right, what you can do is your v, like you have to write v2 by I1. So one thing I know, what is I1 equals to. So from this equation I know what is my I1 equals to. I1 is equals to uh, 2 divided by Z1 plus Z2 into V1. Okay, I1 is equals to 2 divided by Z1 plus Z2 into V1. That is what my I1 is equals to, and I can replace this, right, for the same condition. This is for the condition when my, of course, your I2 is 0. So this is also same condition, right, I2 is 0. So I can replace my I1 here, V2 will divide by V1 into 2 by Z1 plus Z2. Okay, so basically I need to find out the ratio of V1 and V2. So that is very easy, right? So what is my V2? V2 we can write as a sum. Okay, let me convert this. Yeah, V2 can be written. Okay, let me write this as plus minus only. That will be easier for us. V2 can be written as a sum of this voltage plus this voltage, right? This whole potential is across these 2 points. Either you write it in terms of VCV plus VBD, or you can write in terms of VAD and V. Okay, this is VAD. Sorry, this is in terms of VAC. Sorry, this is not AD. VAC. In terms of VAC and in terms of VAD. So I will write, like, I hope you can apply the KVL, right? This is one of the KVL. In terms of V2 you can write, or this is the other KVL. Okay, so your V2 will be equals to sum of this VCV plus VVD. I can apply KVL, right? Simple KVL I am applying. So it is VCV plus VBD. Okay, so that is what my V2 is equals to. That is what my V2 is equals to. So now what I can write? So what is VCV basically? What is VCV? So if you observe, this Z1 and Z2 are in series because no current is coming here, right? No current is coming here, so this Z1 and Z2 are in series. So if these two are in series, basically a voltage division rule can be applied because this V1 is across this whole resistor, correct? Whole combination of impedance. So voltage division rule I can write that my VCV is equals to this V1 into Z2 divided by Z1 plus Z2. So V1 into Z2 divided by Z1 plus Z2. So this is my VCV. Something similar you can do for VBD as well. So again, this combination is in series because no current is flowing here, zero current is flowing, zero current is incoming, zero current is outgoing. So these two are in series. So if these two are in series, V1 is directly connected across the series combination. So I can write that Z1, like it is just like a voltage division, right? So again, VBD, now keep this in mind, this is in the opposite polarity. So I have assumed this to be higher polarity, right? But current is incoming here. So technically this should be the plus terminal, but I have assumed this to be plus terminal. So current is entering. So for a resistor, right? How do you write the polarity for a resistor? So if I have a resistor R here, and if I say current is incoming here, so you write plus minus, correct? because resistor can only absorb power. So current should always be incoming to the positive terminal. Current should always be incoming to the positive terminal. Now, if I would have flipped the current, let's say like this, then how you would have written the potential? This was the potential, because current should always enter the positive terminal, because resistor is a absorbing element. It can only absorb the power, it can never deliver the power. Same for impedance, same for passive impedance. Passive impedance can only absorb the power. So if this is the plus minus, so higher potential is here, so current will flow from higher potential to lower potential. So current can only flow in this direction. But of course I have assumed BVD to be in this direction for my own convenience, because I wanted to write here plus VVD. But actually current is flowing like this, right? So VBD actually will be equals to, there will be a negative sign here. Why will be there negative sign? I have explained here. Okay, because current is in the opposite direction. So here actual current is in opposite direction. Okay, actual current is in opposite direction. So this will be minus V1. So that's why negative sign is there, minus into, now you apply your voltage division, simple, Z1 divided by Z1 plus Z2. So this will be Z1 divided by Z1 plus Z2. Okay, of course V1 is there because voltage division is happening with V1 only. Okay, so now you write your V2. So what is your V2? V2 will be, V1 will be there, and VCB is Z2 divided by Z1 plus Z2 minus V1 Z1 divided by Z1 plus Z2. Okay, so your V2 will be equals to V1 into Z2 divided by Z1 plus Z2 minus Z1. Okay, so from here, of course, what you will write? You will write you replace your V1 here, right? It is a ratio of V1. It is a ratio of V1 by V2. So sorry, V2 by V1. So my V2 by V1 is equals to Z2 minus Z1 divided by Z1 plus Z2. So if I replace here, right, V2 by V1, this will ultimately become my Z21 will ultimately become Z2 minus Z1 divided by 2. Okay, it will ultimately become Z2 minus Z1 divided by 2. So this will be your Z21. Okay, I am just seeing whether I have made any mistake or not. Z1, okay, current is flowing like this, so it will be plus minus, so it is plus, okay, minus plus plus, yes, this is correct. Current drop will be happening like this, current drop will be happening like this. Yes, it is correct. Yes, yeah, so yeah, it is correct only. So I was just checking whether I have done everything correct or not, because somewhere, right, because in my notes what I have written is this formula should be coming with Z1 minus Z1, not with Z2 minus Z1. So somewhere it seems I have made a mistake here. That is what I am trying to understand. Okay, let's find out the other parameters, then we'll see, because this is a reciprocal network, so Z21 should be equals to Z12. Okay, so let's find out the other parameters. So now I hope other parameters will be a bit easier for you to find out. So again, it is a symmetrical network, right? Again, it is a symmetrical network. How it is a symmetrical network? Seems like a symmetrical network. From this portion as well, you can understand this is a symmetrical network, right? This is almost like a symmetrical network. Why? Because you will see that Z11 is equals to Z22. What is your Z22? So to find out Z22, you make your I1 current 0. You make your I1 current 0. So if I make my I1 current 0, so this Z1 and Z2 will be in series. This Z2 and Z1 will be in series. So ultimately your V2 by I2, which is the ratio output impedance will be basically the parallel combination of Z1 plus Z2 parallel with z1 plus z2. So your v2 by I2 will be equals to z1 plus z2 divided by 2. So this will be your answer for z22. What about z12? So again z12, right? Okay, I'm seeing if I can use any KVL or something, trying to figure out. So z12 is v1 by I2 when my I1 is 0. Okay, so v1 by I2. So this I1 current, right? Okay, there is a easier method. Why I was okay? Is there any easier method? No, there is not that much easier method. So okay, this I2 current is here. So what is the current through here? The current through here is simply like, if I2 current is incoming here, it is getting divided by this and by this, and both are offering same impedance. So it will simply be half, right? This current will be I2 by 2. This current also will be simply I2 by 2, correct? So now if I try to apply a KVL throughout this loop, any loop, right? If I apply KVL in this loop, so if I apply a KVL in this loop, so I will write minus V1, this is the KVL, plus, now I'm just using a different method to solve for I1 and I2. So minus V1 and minus V1 plus minus V1. Now what is the direction of the current? Direction of the current is along this, right? So this will be the higher potential. So this will be plus I2 by 2 into Z2. And again, what is the direction of the current? This time the direction of the current is like this. So I am going in the opposite direction. Okay, I'm going in the opposite direction. So direction of the current is like this. I'm going in the opposite direction. So this is plus and this is minus. So of course my KVL convention is, if I encounter whatever sign I encounter first, that I will write. So this will be minus I2 by 2 into Z1 equal to 0. So from here my V1 equals to I2, if I take common, this will be Z2 minus Z1 divided by 2. So okay, we derived it correctly only, so that was also correct. So here my V1 by I2, so this is also another way which you can solve. So I am explaining all the ways, all the methods which you can solve the parameters. So there are many ways, right? Solving a network, there are in like n number of ways, but of course you have to choose which one will give you the fastest result and which one will be the optimized one, because which one will take the least effort, okay, and least effort and time. So how will you know about that, which method to use? With practice. You practice more questions like this, so automatically you will understand when to use what kind of method. So I quickly understood that if I used that previous method, it was going lengthy, so I changed my what do you say, I changed my method, I changed my way to approach the problem, I changed my approach. So this will be V1 by 2 will be Z2 minus Z1 by 2. So whatever we have derived, right, it is equals to Z12, which is equals to Z21. Of course the network will be reciprocal because it consists of purely passive elements. So if a network consists purely passive elements, it will always be reciprocal, it will always be reciprocal. Okay, so yeah, that's how you solve. Of course you can simplify this circuit, and from there also you can solve. That is the homework for you. Simplify this circuit, method 2, using this circuit you solve. Okay, simplify and all those things, this will be a bit easier, but of course doing that conversion will be a bit time consuming, and of course you don't want to do that. Okay, so yeah, yeah, that was about for this question. Now just one last topic that is left about the model. Okay, so Z parameters can be modeled like this. So here, right, what I observe is V1 is being written in terms of two currents, I1 and I2. So it is like a KVL equation, KVL 1 and KVL 2, because voltage is written in terms of the voltage drop, right? So both are KVLs. So in the first KVL I have this input current and the output current as well, and in the second KVL also I have this input current and the output current. Okay, in both the KVLs I have the input and the output currents. So simply, right, we can model our Z parameters like this. This is just a way to represent, model means way to way to represent mathematical equation in circuits. Way to represent mathematical equation in circuits. Okay, this is not unique. Not unique. Keep in mind, this is not unique. You can represent many ways. Basically, what do I mean is, like, if I have a z, if I know the z parameter of a network, I cannot say what are the networks. Okay, what is the exact network, what is the exact places of elements. So let's say I have a z parameter of a network. V1 equals to 2i1 plus 3i2 and V2 equals to 5i1 plus 2i2. So if I say the z parameters for this networks, n1 is this, and for n2 also it has the same z parameter, but I cannot directly say that what are the elements. If network n1 is something like this, okay, network n2 can be something totally different. It can have dependent sources, something totally different, right? And my drawing is very bad, please ignore my drawing. So network n2 will be something really different, right? And still they can have the same z parameter. That is totally possible. You will observe that as well. So you cannot uniquely say that if network 1 is this simple resistive network, network 2 also will be this simple network only. No, it can be something else. Yes, their z parameters are same, both of them have the same z parameter, but it really does not matter. It really does not matter. Okay, it really does not matter what is their z parameter. I cannot uniquely draw the circuit. Okay, I cannot uniquely draw the circuit. So that's why this is just a one way to represent, and this is not that important. Just, of course, I am educated, so I have to teach you everything. So this is how we model, and this will not be used anywhere. Trust me, this will not be used anywhere. This will not be asked in examinations. Okay, so yeah, that's about it for this lecture. So with this, we have finished our z parameter total chapter of z parameter. In the next chapter, we will discuss about y parameters. So I hope you have enjoyed this lecture. If you did, make sure to hit the like button and make sure to comment down below which portion you enjoyed the most, and I will see you in the next lecture. Until then, happy learning.